let's take a look at the first section, which is 3.7. There's not very much on it. It's basically amounts to putting something in on the calculator and finding an intersect. So I'm going to go through it pretty quick. So remember that when you're solving a system of equations, generally means you're solving for a minimum of 2 variables. Could be 3, 4, 5 variables. We're going to focus on 2 variables in this section because we're doing graphing. And graphing, unless you're going to get into 3D graphing, really the limit to graphing is 2D. So we're going to focus on systems of 2 variables. So that means once you find one answer, you have to go back and find the second answer. Substitution and elimination are ways you can solve systems. But we're going to focus on equations that might not be as easy to solve with those methods. Okay, so we'll look at how to do it graphically. So that means most answers in this section will be approximate. Okay, we'll be rounding them off. When you solve a system that has 2 variables as an answer, you like an x and a y, you can write the answer as a coordinate or ordered pair. Or if I set it up on Edge Elastic, I might just put 2 boxes. X equals, put a box, y equals, and then another box. You can really do it either way. Right, so graphically, when we're solving a system, it's basically where the graphs cross. If you're solving a linear system, meaning 2 lines, how many places can 2 lines cross? There's different cases. Yep.
1. If they're going straight, if they're linear.
Okay, they could cross in one spot and make like an X shape. Yep. Could be how many?
None.
None. What would have to happen for the lines to not cross?
Same slope.
Yep. They have to have the same slope and different y-intercepts, so they'd be parallel. Or there's one more case that can happen with just 2 lines. Yep.
Cross at every point.
Right. They could cross at every point because they're the same line. Okay. So any of those 3 things can happen with linear systems. When you get into non-linear systems, all kinds of things can happen. Like if you draw 2 parabolas, they could possibly not cross at all. They could cross once. It depends. All right, so let's try this. If we want to solve this graphically, what do we have to do to both of these equations? Yeah.
We've got to first start by moving the x over, and then we got to divide by the number that's next to the y.
Right, we got to get y by itself. So the top one, we're doing what was just said, trying to do it all in my head. You would minus the 2x and then divide everything by 3. So minus the 2x, divide by 3, and then you still have the 5, and that would also be divided by 3. So any questions on getting y by itself in the top one? Okay. How about if you get y by itself in the bottom? What would y be there? Yep.
Plus 21.
Yep. So you'd add the 3x to the other side, but then you'd divide by 5. And then you would have the 21 on the other side, and that also would be divided by 5. Okay, when we draw these, what kind of shape is the top and the bottom one? They're both what?
Linear.
Yeah, they're both linear. It's just y equals mx plus b, and they have different slopes. So how many times are they going to cross? Yeah, they're going to cross 1 time. So there's a couple different ways you can type them in because they are fractions for the slope. I'll do each one different. So the first one, I'll do it like this. Let's do negative 2/3 x plus 5/3. You can do it that way. Or if you just want to multiply the slope and the x together, you could write it as, let's do 3x over 5 plus 21/5.
You could just use that fraction feature of these. You have that.
Yeah, you could. There is also a fraction button on some calculators, depending on what model you have. Yeah, but if you want to type it in, either one of those ways will work. Okay, so there's the first one, and the second one. And we said earlier that the answer is where what happens, where they intersect. How do we find an intersect? Yep.
Second calc, and then we press 5 for intersect, and we just push enter 3 times.
Yeah, you can just push enter 3 times. The guess isn't going to matter because there's only one spot where they cross.
If there were multiple spots where they cross, then we'd have to put it closest to the crossing point that we were trying to find.
Correct. Yep. And there's your answer. So if you want to write it as x equals and y equals on 2 separate lines, you can. Or what's the other way I said you could write it?
Ordered pair?
Ordered pair. Yep. So it would have to be in that order because it's an ordered pair. There's an order. So -2, 3. Okay. Any questions on that? All right, so that's linear. Let's look at this one. Okay, this one they just want us to find the number of solutions. We're not actually finding the solutions. Now, the top one is what type of polynomial? How would you classify it based on its exponent?
3rd degree polynomial?
Yep, 3rd degree, so cubic. And what about the bottom one?
Square polynomial?
Which would be, what do we call that one?
2nd degree polynomial?
Yeah,
Right.
or quadratic.
Yeah.
Okay, so we got -x cubed plus 3x squared plus x minus 3. So a cubic and a quadratic, they could cross. It's kind of fancy. A lot of different things could happen there. Let's see. 2x squared plus 5. Make sure we typed it in right. Okay, and let's hit graph. I'll do zoom 6. And we're looking for how many times these 2 graphs cross. Okay, so there's one. Well, one graph. Here's the second one. Okay. So how many solutions does it look like there are?
2 or maybe 3 that we don't see.
Yeah, we got to make sure we zoom down. It kind of looks like to me the red and the blue are getting closer and closer as they head down. So I bet if you set your y min at like -30, you'll probably see that they cross a 3rd time. So even if an answer is off the screen, it still counts as an answer. You have
We
to.
need to put it even further.
I need to go even further.
Yeah.
This will probably be enough to give me an idea, but you're right. I got to go a little bit further, but I can tell they're going to cross. Okay. Any question on that? So we would say that there are 3 solutions. That's that one. And let's just do this one algebraically. Okay, we've done graphically. Graphically, it's already set up for you. Just put the top one in y1, the bottom one in y2, and see where they cross. But let's try it algebraically. What method would make the most sense here if I want to solve this algebraically? Yeah? Yep, I would do substitution. Take what y is equal to, and then plug that into the other equation. You don't even have to do any work to get a variable by itself. It already is. So just take what y equals and plug it into the bottom equation. All right. And now when we try to solve something, what do we generally get it equal to? Yeah, there you go. Yeah, 0. You get it equal to 0. So let's write x cubed minus 4x equals 0. And what can we do with the left-hand side?
We add 4x to the other side.
No, we want to keep it equal to 0.
Is it possible to factor that?
What could you factor out of that?
Yes.
Okay, we can at least start with that. And how does x squared minus 4 factor?
X plus 2x minus 2.
Yeah. So honestly, not that bad of a problem because it factored all very nicely. So what would be your 3 answers that would make each one of those factors 0?
It would be 0, 2, and -2.
0, 2, and -2. And you could confirm it by graphing y1 and y2, and that should be the 3 x values where they cross. Now, you should actually be a little bit careful how I write this. Let's make a table for our answers. So x is 0, -2, or 2. What else do I still need to find? Yeah? I still need to get the y values. I'm only halfway done. I have the x's. Well, just take all the x's and plug them in to get the y's. Either formula will work, but I think one of them is simpler.
It'd be better to do the bottom one because it's just the x times 3.
Yeah. Just take the x and triple it, and that's your y value.
It's better than
Yeah.
cubing it.
So those are your answers. 6 different numbers, 3 different coordinates. Any questions on that one? Alright, so that's all that was really in 3.7. Okay, just solving. It was graphically. I decided to do the last one algebraically, but you could have done it graphically. Alright, so the rest of the week we're going to spend on 4.1 and 4.2. Okay, 4.1 and 4.2 are all about rational functions. So as an example, that's a rational function because it's a fraction. That's an even simpler rational function. That's another rational function right there. So we're going to talk about how you graph rational functions, what this number does, like how does it shift it? Is it 2 units left or right, or 2 units up or down? And then we'll talk a little bit about solving rational equations, but that's not until section, I think it's 4.3 that we get to that. So that won't be till next week. So this week, mostly graphing. So a rational function is a fraction that can be written in the form p of x divided by q of x, where p of x and q of x are polynomials. And of course, the bottom polynomial can't be 0. So an example of a rational function, 2x cubed plus 8x minus 4. That's a cubic polynomial divided by x minus 3. That's a linear polynomial. Right, so any polynomial in the top and any polynomial at the bottom except the 0 polynomial. Don't put that in the bottom. Yeah.
One of the ones that wouldn't work for that equation would be 3 because of -3 right there.
Right, so this is fine for a rational function. But then we have to talk about, are there certain values you can't use in it, which 3 would be one of them. That's actually going to be what we call a vertical asymptote. So we're going to talk about asymptotes, both vertical and horizontal in this section. But that's good. We've got to be able to figure out the values you cannot use in the bottom. Okay, here's a couple more examples. Not doing anything special with them, but those are rational functions. How you end up graphing them really depends on the degree. If the degree in the top is bigger than the degree in the bottom, we're going to learn how to do something. Or if the degree in the top is less than or equal to the bottom, we're going to do something a little different. So this bottom one we'll talk about when we do 4.2 part 1. This top one we won't talk about until Thursday. That would be 4.2 part 2. Yeah, but they're both rational functions. Any questions on that? So the domain. Well, it's pretty straightforward. It's a fraction, and the only thing you're not allowed to do with a fraction is plug 0 in the denominator. So the domain is all real numbers, except numbers that would make the bottom 0. Sometimes there's one number that would make the bottom 0, like in this top one, it's just 3. If the bottom is a quadratic, it's possible that you have how many answers that make the bottom 0?
Quadratics are 4 polynomial 1, so it would be 4. But since
Quartic would have 4, but quadratic could only have up to 2. Yeah. And it is important we know how to find these, whether that means using quadratic formula, factoring, or even the rational root theorem with synthetic division. I don't think did we talk about that yet? Rational root theorem, synthetic division?
I think so, yeah.
Yeah, we talked about.
Did about okay. So we might have to use that as well. Hopefully factoring because that's the quickest. Yeah.
Two things. So synthetic division is the thing where you have the box and you have there's a number in there, and then you have the line of numbers.
Yeah.
That you remove the powers, but you put it in the 3 to 0. You fill in the numbers that aren't there, and so then you drop it down. Then you apply it. That's what you do synthetic division. The rational root theorem, is that the P's and Q's thing?
Yeah.
Okay.
Yep. Okay, so find the domain of the following. I like to figure out what number you're not allowed to use, and then go from there. Okay. What would be the domain, or what's the number that you can't use in this one? Yep. 3. So, does anybody remember as an interval, how do you write everything except 3? It's going to have the U symbol, and then 2 things. Did you know? Yeah?
Parentheses, negative infinity, comma 3. Another parentheses,
Yep.
3, negative infinity.
Perfect. So that's how you write as an interval. You can pick anything lower than 3, anything higher than 3, but the parenthesis means not 3. Okay, that's it. That's the domain. I should put that word though. So write down the word domain and then put what the domain is. Okay, let's look at this one. Again, it's just what would make the denominator 0. So to figure out the zeros of the denominator, what do you think we're going to want to do with the denominator first? If it's factorable, that's going to be the best thing that we can do. If it's not, we're going to have to use quadratic formula to figure them out. Okay, so my first 2 terms would be x and x. And then what about my numbers in the parentheses?
one of them would have to be a negative, and the other would be a positive because the constant is a negative
Yep.
1, so when multiplying it, would you do
Positive 2 and negative 1.
Yeah, I would do positive 2, negative 1, and let's just check it. X squared plus 2x minus 1x is 1x. Perfect. Now there's going to be 2 values that we can't use. Let's just put those off to the side. The 2 values we can't use, 1 and negative 2. Now, if I wanted to write that as an interval, think about it like it's on a number line. You can't use this one, and you can't use this one. So how many sections would you have to write down as intervals? Yeah?
3.
3. Yeah, you need 3. Can you tell me the first section?
Negative infinity to negative 2.
Yeah, negative infinity to, what is it?
Negative 2.
Negative 2.
Also, quick question. When you say all reals for domain, can't you just have the symbol of the triangle and R on the side to show all real numbers, and then you say except the? Because in the past descriptions it said you said it's all reals. So instead, for the homework or for a test, could we just write the R symbol thing?
It depends on if they want you to write what the domain is or what it isn't, and then the format. They could ask for it as an interval, and then this is really the only way to do it as an interval.
Okay.
If
Well,
they ask for it as like an inequality, then you could also do it. You could do it a little different.
what situation could you do the R symbol?
I guess if you were writing out like a sentence, you could say the domain is all real numbers, or use that symbol, except 1 and -2.
Okay.
So if it said like describe the domain as a sentence, then you could write what you said. So we got -infinity to -2, or
Next would it be -2 and 1?
-2 to 1, or 1 to positive infinity. Basically, however many numbers you can't use, you're going to have one more interval than that. So if there's 2 numbers you can't use, you're going to have 3 intervals. If there's 1 number you can't use, you have 2.
What does the U stand for?
What does the U stand for? There's technically a U, and then there's that symbol. They're different symbols.
I don't know what I was going to say.
The U is or, and this symbol is and. Yeah. We don't say and because and means it can be in both at the same time. You can't have a number that's here and here. It can be here or here. So kind of technical, but it is an or, not an and. Okay, and let's look at this one. This one, let's just write it as a sentence. Okay, we've done a couple with intervals. So the domain here would be what as a sentence? Yeah.
X is less than. X is greater than 2. And X is less than -4.
X could also be 0 though, and I don't think that fits into what you said. Greater. What did you say? Greater than 2 and. Oh, you said greater than 2
Yeah.
and less than -4. So you're over here. Yeah, there's some stuff in the middle that it could be though as well. Like 0 would be okay. Yep.
The domain is all real numbers except 2 and -3.
Yeah, I would just say it like that. You could say the domain is all reals, or you could use the symbol for all reals, except 2 and -4. If you wanted to say it the way you were going to say it, you could say the domain is all numbers that are less than 2. Oh no, all numbers that are less than -4, between -4 and 2, or bigger than 2. It's kind of wordy to say it. If we're going to say it that way, I would just write it as an interval.
Yeah.
If you're going to write it in words, it's easier to use the word except than to write out those intervals. It just starts to get a little wordy. So both of those were rational functions, but this is the simplest rational function, sometimes called the parent function. It's the most basic one that you can have. There's no transformations done to it. Let's graph it on the calculator and just see what it looks like. Just clear everything out. Let me go back to Zoom 6. And the calculator doesn't quite draw it perfect. It's pretty good, but. Okay, so here's your graph. And if you look at it, it almost looks like it stops, right? It doesn't. Okay, the graph continues in every direction, up, down, left, and right, forever. So if I want to just kind of modify that a little bit to fix it, this part should keep going up, that part down, and the left and the right did pretty good. The problem with the middle, towards the middle, is it starts to get so steep when something moves almost vertical, the calculator gives up drawing. Okay, but that's what it should look like. And that's the graph of 1 over x, the simplest rational function that there is. Now, as x approaches infinity means as you head which way on the graph?
To the right.
To the right. And as x approaches negative infinity?
To the left.
To the left. The same thing happens. As you head further and further to the right, or further and further to the left, what's the y value getting closer to?
It's getting closer to 0, but
Yeah.
it can never reach it because if you're dividing something, you can never get a 0 out of it.
Right, no matter what you divide 1 by, it'll never be 0. Even if you divide 1 by a billion,
And
it's
you can't,
small.
and you can't divide it by 0 either, so
Right, we'll talk about what happens when you try to divide by 0, or something close to 0. But what we're looking at in this case is what happens as you head further and further away from the origin. No matter which way you head, the y value is approaching 0. So if we were to graph y equals 0, okay, right on top of the graph we have, okay, let's just put y equals 0, and I'm going to make it a thin line, and we'll make it dotted. Now, it's kind of hard to see because it's on the axis, but you can actually see that it's dotted in here a little bit. I can see it up close. But that line at y equals 0, that's called an asymptote. Okay, specifically, this is a horizontal asymptote. So part of what we do in this section is we write the equations for 2 kinds of asymptotes, horizontal and vertical. Remember, when you write a horizontal, it has to start with y equals. So if that was a multiple choice question, and I said, tell me the equation of the horizontal asymptote, I would probably put y equals 0 as a choice and x equals 0 as a choice. X equals 0 would be a vertical.
Isn't there a horizontal and vertical asymptote in this scenario?
Yeah, we're going to talk about the vertical in a little bit. So for now, just the horizontal. And remember, asymptote is a line that a graph gets closer and closer and closer to as you head to infinity, but it never hits it in this case. It just gets closer and closer. So the way that you find a horizontal asymptote is you look at your graph, or you look at the formula for it, and you imagine what happens as x gets bigger and bigger and bigger, either as a positive or a negative. A lot of times if it's a complicated graph, I'll put it in the calculator, and then I'll zoom out so I can look further and further to the right. Or I can just use the table. I can imagine plugging in a really big number for x in the table, and it'll tell me what y is. But I'd say a lot of them are going to be simple enough. We can do it without a calculator. These are all different kinds of asymptotes. The first one is pretty similar to what we had. This is a graph that's curving up towards it. The second one is a graph that actually crosses the asymptote. No rule saying you can't cross an asymptote. The idea, though, is as you head further and further to infinity, you get closer and closer and closer to it. So maybe you do all kinds of stuff early on, but then eventually you start getting closer and closer and closer to something as x goes further to the right or to the left. In this case, it doesn't look like there's an asymptote on the left side. I don't really see anything, but I do on the right. Any question on that? Okay, I think there's some pictures on the PDF on page 217, the same pictures. There might also be one more. I'm not sure. See if we can find the horizontal asymptote without a calculator. So remember, horizontal asymptote is what happens when x gets really big. So imagine plugging a really big number in for x right there. Okay, like 1 million. what's going to happen to this? Just the part I put a box around.
It'll get smaller.
It's going to get smaller. As x gets bigger and bigger, this box gets smaller and smaller. And when we say smaller, what's the box going to get close to?
2.
The box?
0.
0. So the box gets very close to 0. And if you take something very close to 0 and add 2 to it, what do you get?
Very close to 2.
Very close to 2. So your horizontal asymptote, which is never reached, is y equals 2. And if you were to graph this, you would see exactly the function that we did the first time. That's 1 over x. But what do you think the plus 2 on the end is going to do? When you add a number on the end of a function, like we did this with parabolas, what does adding a number at the end do? Yeah?
It'll shift the whole function. I'm assuming it'll be like up.
Up. That would shift the graph up 2. Yep. This would shift the parabola up 3. So adding or subtracting on the end shifts it up or down.
So does that mean that the asymptote be 2?
Yeah, the asymptote would be at 2. If you don't shift it, it's at 0. But since we shifted it up 2, the asymptote shifts up 2 as well. Yep. Okay, let's try this one. So again, imagine plugging in a really, really big number for x. Think about what's going to happen to what's in the box. Think about what it gets close to. And then subtract 3 from that. So what happens to that expression, the whole thing, as x gets bigger and bigger and bigger? Yeah?
It goes closer and closer to -3.
Yeah. And since it's a horizontal line, how would you write that?
Like on a graph.
For my answer in that box.
X equals y equals -3.
Y equals -3. Yeah. Okay, so that's the equation of the horizontal asymptote. Any questions?
The actual value for the line can never be 0 or -3, but the asymptote can be exactly that.
Yeah, so the asymptote is as you head to the right or to the left, what is the curve of the graph going to basically level out at?
But the graph itself, like the line will never actually touch that.
No, it will not. It will not touch -3. So the range of this graph would be every single number except -3, because it's going to go up forever. It's going to go down forever. It's just not going to ever hit the number that the asymptote is at. Yep. Okay. You don't really need to sketch that. That's fine. All right. So sometimes we can have 2 horizontal asymptotes. Let me see if we're going to do one. Yeah, I'm not worried about that one. I'm gonna hold off on that one. All right. So now we talked about the horizontal. Let's think a little bit more about another kind of asymptote. What number are you not allowed to use for x in this case?
0.
Yeah, you can't use 0. So I want to look at what happens not when x is 0, but as x approaches 0. Now you can approach 0 from 2 directions. Right? Here's 0. You can either come at it from the positive direction. Okay, positive numbers are on the right. So you can approach 0 from the positive side, or you can approach 0 coming from the negative numbers. So you can come at it either way. Let's see what happens as we approach 0 from the positive side. So what's a number that's really close to 0 coming at it from the positive side? Yep.
0.0001.
Yeah, like 0.001. So if we put that in the calculator and we press second table, okay, mine's not set up to let me plug in that number that was just said. So yours should be all set, but I have to press second window. Might have shown you this before, I'm not sure. Did I show you this before?
I think you showed it once.
Okay. So if you go to second window, I want to let it ask me for the x value. I don't want it to automatically give me one. So I'm going to have it ask me. I'm going to press second table. Now I can plug in 0.0001. What's going to happen if I put in 0.0001 for x?
Why that is gonna go pretty high.
Yeah, the y value is going to go really high. Okay, when I plug in 0.0001, I get 10,000 for y. The smaller I make x, the bigger y gets. And it approaches infinity. Okay, so as you approach 0 from the positive side, the y value goes way up. And what about if you approach 0 from the negative side? Like if you put in negative 0.001, what would happen to the y value? Yeah.
It's gonna go very far down.
It would go
Or it's
down.
gonna move in.
So this is the symbol that means to approach 0 from the positive, from the right side. When you put a little minus on a number, that always means from the left side, because negatives are on the left. So when you have a graph that you can approach a number, and all of a sudden as you get to that number, it kind of like curves up to infinity, or down to negative infinity, or even something like this. There are graphs where both of them curve up together. We haven't looked at one yet. But if you have a behavior where all of a sudden it curves up or down, that's a vertical asymptote. And this is why we spent so much time in chapter 3 learning how to set an equation equal to 0 and solve it, because that's how you find vertical asymptotes. You set the denominator equal to 0, and you solve. All right, so that's just more of a visual description of what's happening. As you approach a number from the left or the right, if it curves up or down, that's a vertical asymptote. And I think I'm going to write it in a second, but it's where the denominator equals 0. I think that's the next thing. So if I had something, let's just say I had something like this. Think of the number that you can't use for x, and that's the vertical asymptote. So what number are you not allowed to use for x there? 4. So if you graph that on the calculator, show you what it looks like. Type in x plus 3 divided by x minus 4. As you get close to 4, the graph is going to curve up and down. Okay, so there's your vertical asymptote at 4. Now, what if I change it? See if you guys remember what this does. What number am I not allowed to use for x?
4.
Yeah, same number. What's going to happen now?
It's going to cross cancel. So it's going to make the entire thing 0 because if you plug 4 in, then that makes the factor on the bottom 0 and when the factor is on top 0, meaning that no matter what you get, like in that case it'd be 7 to be 7 times 0, meaning that the entire equation would equal 0.
Well, we can't use 4 though, because that still causes you to divide by 0. So that would be undefined if you try to put in 0. But what happens? Anyone remember? Yep.
Wait, can you not do it by 0? Because then each will be -4 and then they'll just like cancel out.
But you could plug in 0. Yeah, if you plugged in 0 for that, you'd get 3. 0 is an okay number to plug in. But what's going to happen when you plug in 4?
Do you get 0 on the bottom? And you're just not supposed to.
Well, yes, it's going to be undefined. So let me change my question. How's the graph going to look?
Completely vertical? Like a vertical line.
No, the graph won't be a vertical line. Something special is going to happen on the graph. We've talked about this before.
Piecewise?
No, it's not going to be a piecewise function. There is going to be a discontinuity. Yes. Can you be more specific? A vertical asymptote is a discontinuity, but you're not going to have a vertical asymptote here. Even though 4 is a value you can't use for x. Anyone have a guess? I know that's not exactly how I wrote it, but it's the same thing.
Are you gonna have that thing where like it looks like it could be like it'll look like a line, but it's really a discontinuity. It's just not shown.
Yeah, what's in that graph that we can't see?
There's like a tiny hole.
There's a hole, yes. So just because you find a value that you can't use doesn't automatically mean it's a vertical asymptote. It means it could be. Once you find a value you can't use, then you have to check if the top and the bottom have a common factor. If there are no common factors, you will have a vertical asymptote. So that's very important. If the numerator and denominator do not have a common factor, you'll get a vertical asymptote where the denominator is 0. If the numerator and denominator do have a common factor, then you will get a hole at that number instead of an asymptote. So if I put that question on a test and asked you, what are the vertical asymptotes in this problem? What would you say?
There are none.
There are none. If I said, what are the values you cannot plug in for x? That's a different question. What would you say for that?
4.
4. Yep. Okay, so when we're writing the equation of a vertical asymptote, it always starts out x equals. And then it's just the value that would make the denominator 0. There's no common factor here. Just a 1 and an x minus 2. You'd have to have an x minus 2 in the top to get a whole. So what number can you not plug in for x?
2.
That's your vertical asymptote. And we talked about what adding or subtracting a number on the end does. That shifts it up or down. What do you think adding or subtracting a number inside the denominator does? Doesn't shift it up or down. Yeah? It's going to shift it left or right.
Is it like opposite?
But it's opposite, right? The horizontal stuff is always opposite. So minus 2 is going to shift the graph to the right. Yes. So this would be a horizontal shift of that graph 2 units to the right. Yep. That's why the vertical asymptote, which was at 0, is now 2 units to the right. Okay. How about this one? What's the vertical asymptote going to be here? Yep.
-1. Because the vertical one's on the outside, right? And
Well, this is a shift down 1, but does shifting something up or down affect vertical asymptotes?
oh yeah, sorry.
Right? If you got a line that goes up and down forever like that, and you move it up a little bit.
Yeah, I was thinking about the opposites. The vertical would be -3.
Right. Vertical asymptote is x equals -3. What if I did that?
Still be the same.
It'd still be x
Yeah.
equals -3. This shifting vertically changes what asymptote?
Ooh.
The horizontal.
Changes the horizontal. So,
I was just thinking because like it changes the horizontal and vertically. Like it changes its height. So I was just
yeah.
thinking that.
So if I asked you to describe the two transformations here, the +3 is shifting it Left, how many?
3.
3. And the minus 1?
Down 1.
Down 1. All right, let's. I want to see if I say that anywhere. I don't think I do. So it's probably good for me to kind of keep reinforcing that. What if I? All right, let's do something like. Try to use the letters in the order we would do them. So there's all the transformations you could have. Sometimes you see the 1 and the C multiplied together and they just put the C in the top. But what's A going to do? Again, that's going to shift left or right. Okay, let's jump to D. All right, what's D going to do? Yeah, that's your shift up or down. How about C? Multiplying by a number in front. Multiplying is never a shift. And this is in front, so it's outside. When I say outside, anything that's in the green, that's inside. Anything that's outside the green is going to do something different. So you got an example of inside, what happens, and an example outside. So what do you think the C?
Doesn't C make it bigger or smaller?
So how are you going to word that as a transformation?
Like a scale factor?
Okay, I need a little bit more specific. But I think you're on the right idea. It could stretch or shrink, but I need a little bit more. So could be stretch or shrink. Someone be more specific about C? Yeah?
Narrow or wider, that it will it will
You can say it in 2 words.
increase with
It could. So could be.
Is it this, change the space between like where like 2 curves come, like how wide?
So I need a which axis does this affect? Like shift left and right, I know that that's a horizontal type of thing. I know shifting up and down is a vertical type of thing.
It's going to be a horizontal thing. Because like, if you're stretching it, it's going to be like
It's on the outside. So anything on the outside of your function is a vertical thing. Yeah.
It would make the graph, like, pretty sure sharper, like, its movement, or no. If the number is...
So people aren't quite getting what I'm looking for here. It's a vertical stretch or shrink. So usually the way we describe that is vertical stretch by a factor of, and then we say the number. So because it's on the outside, C and D are both on the outside, it's vertical. Anything on the inside is horizontal. Adding or subtracting is always a shift. So what do you think B is going to do? It's multiplication, but it's on the inside. Yeah?
Wouldn't that stretch it along the horizontal axis?
Yeah. It's going to be a horizontal stretch or shrink. Now remember, everything is backwards with the horizontal stuff. Vertical, it's not. So if you did something like this, I would say that's a vertical stretch by a factor of 3. If you did something like this, that's a horizontal compression by a factor of 3. Now, if you don't want to say compression, I guess you could say stretching horizontally by a third. Stretching something by a third really means to compress it.
Wouldn't that be shrink it by 3?
You could say shrink by 3 or stretch by a third.
Alright.
It's like kind of like saying multiply by 1/3 or divide by 3.
And then
It's the
if it
same
was
result.
0.5x, you would say stretch by like a half.
So, yeah, the bigger the number, the more compressed it gets. The smaller the number, the more stretched it gets. So in that case, that would be a
Horizontal stretch by 0.5.
Horizontal stretch by 1/0.5 or 2. This is going to double the width. This is going to make it 1/3. Okay, this is a whole number. It's going to make it 1/3. This is going to be 2.
So you could just say it shrinks by 0.5.
You could, yeah, that's almost like a double negative though. That's like saying you don't not have homework tonight.
Yeah.
So if you say shrink by a 0.5, it really means
Stretch by 2.
by stretch by 2.
Okay.
Yeah. It's easier to just think of it as stretch by 2. Okay. Now, what about if C or B was a negative? What does the negative cause the graph to do? Yeah, reflect over an axis. If C is negative, it's a vertical reflection. If B is negative, it's a horizontal reflection. So the transformations are exactly the same as every function that we've studied up till now. But just kind of a reminder of how they work. Okay, so find the horizontal and vertical asymptotes, and then describe the transformations. So you really have to have something that's written like this. It has to be broken down so there's a number in front, a 1 in the top, something like that at the bottom, and then plus or minus a number at the end. Does this one have a 1 in the top?
No.
No. So we got to fix it. How can I fix this? We talked about this back in chapter 3. Like, what can you do there?
Fact.
It's already factored. There's nothing really you can factor here because they're both linear. So there's nothing you can factor out.
Substitute division.
Is that a 1 to
What kind of division?
Substitute division.
What's that?
Isn't that where you get the P and Q?
Oh, the rational root theorem? No, we don't have to do rational root theorem. I thought you were almost going to say what I thought. Yeah? No, more something with division.
Oh.
Yeah? You can do synthetic division
That's what, yeah.
or long division, but that's the only way to make that look like it should. So I would do synthetic because it's going to be quicker. So I would put 5 on the outside, and then we're going to put what numbers on the inside?
-2 and 13.
2
-13.
and -13.
Okay.
Here's your first degree term and your constant. There's no other term you're missing there. All right. So what's the first thing we do?
We drop down to 2.
Bring down the 2. All right.
Multiply by 5.
Okay.
-3.
10. And then we get -3. What's the -3?
The remainder.
The remainder. So remember how you can write your answer. Quotient
The remainder.
plus remainder over the original denominator. Okay, that's how you can write any answer to a long division problem. What's the quotient in this case?
2.
2. What's my remainder?
-3 over 5. Or x minus
-3 over what?
x minus 5.
Now this is looking a lot more like what I just talked about, where we can see the transformations. I'm going to fix that a little bit. I would think of it like this. I usually put the vertical shift at the end. You don't have to. And then, how could I think of this as a 1 over? I want to put my C value in front. So what would be my C value?
-3.
Right. I would do -3 times. And now you've got it written exactly the way you need it to describe what each number is doing. And the other thing you could do is you could put that in y1 in the calculator. You could put that in y2, and they should look identical. Okay. So how many, well, let's actually write down what do they want first. The horizontal asymptote. Let me move this so I have a little space. Okay, what's going to be my horizontal asymptote? Let x get really, really big and tell me what's going to happen. Yep.
I just had a small question about the shifting. On the inside side, if the b would be negative, it's a shrink.
The b?
Yeah.
So I forget, where was b? In front of x?
Yeah.
So the bigger you make b, the more compressed it gets.
Okay.
So if you make b 10, that would be a horizontal compression by 10. Or stretch by 1/10. Same thing.
Why would it be by 1/10?
If b was 10. The bigger you make b, the more squished it gets.
Wouldn't it be back by 10?
If b was 10, yeah, it would make it 10 times more squished.
And 0.1 would be 10.
That would make it 10 times more stretched. 0.1. The smaller you make the number, the bigger it gets. That's how horizontal works.
No, you said that if it was 10, it would be compressed by 1/10.
If it was 10, it would be compressed by 10. Or stretched by 1/10. Same thing. It's kind of like me saying divide by 2 or multiply by 1/2.
So
Say,
So on the outside, if it's a positive, it's stretching. It's vertically stretching.
yes, if C is a positive, like what we're going to talk about right here, that is a vertical stretch.
And if it's positive on the inside, it's shrinking.
Yeah. Well, if it's bigger than 1, it's shrinking it. Like 2, 3, 12, 50 would shrink it 50 times as much. All right, what's my horizontal asymptote here? Yep. You're thinking vertical. Remember, horizontal is what happens when x gets bigger and bigger. 2. Right? As x gets bigger and bigger, this whole thing right here basically just disappears. Like if x was 1 billion, you'd have 1 divided by a number a little less than 1 billion. That's almost 0. Times -3 is still almost 0. So your horizontal asymptote is basically just controlled by that last number. And then how about the vertical?
5.
5. Yep. Okay. How many transformations are happening in that graph? It says transformations. Yep.
It's 5 units to the right.
Okay. So yeah, we can start writing them. So it's going to be shift 5 units to the right. Yep. Shift 5 right. Okay. What's the next thing that's going to happen? Yep.
It's shift 2 units up.
That's D. That's the last thing. So the letter I used A, B, C, D. That's the order you have to write them in.
Oh, you want us to? Okay.
It has to be. Yeah. It's kind of like PEMDAS. If you do a different order, it doesn't always work out. So shift 5 right.
Even if we're just like listing them, I thought we were just listing them.
So generally, when you list them, you have to list them in the order they would be applied.
Okay.
Yeah. Yep.
Shrinks by 3.
So this is a vertical. Remember, vertical, what you see is what you get. So it doesn't do the opposite. Yep.
B would be in front of X, but there's no transformation.
There is no B. So you're right. There is no horizontal stretch or shrink in this case. So we go to C. And what's that gonna do? Yep.
Shrink 3 units.
Mm-mm. Remember, vertical, when it's bigger than 1, it's a stretch. Vertical and horizontal are opposites. Horizontal, everything's backwards. Vertical, everything is not backwards. Vertical, it's exactly what you would expect. This is a vertical stretch by a factor of 3.
Negative doesn't change. Does it?
The negative does something very important. Well, I haven't written that yet.
Yeah.
Yes. Vertical stretch by a factor of 3. The negative has no effect on that. What does the negative do?
What direction? So like it would go downwards, so it would go like this, not up.
Well, remember, it's not a parabola.
Oh
Yeah, it doesn't have it's not a parabolic shape. So we got to describe it as a transformation. Yeah.
So it would flip over the x-axis, and it would shrink the.
Stop there. Don't say anything else. You're good. Flip over the x-axis. Anything else you say up to that point with the negative would be adding too much. All it does is flip.
Well, what about the stretch? Oh, never mind.
We already took care of that.
Alright.
So we already did the stretch, then we did the reflect, and then what's the last thing that happens? Yep.
The last one of the things is a shift up by 2.
Yeah. So we need to brush up on that a little bit. So remember, vertical, it's what you see is what you get. Positive is up, negative is down. Horizontal, negative would move it right, positive would move it left. That's backwards. Same thing with the number you put. When you put a big number for a vertical, it stretches it bigger. When you put a small number for a vertical, it compresses it small. With horizontal, it's backwards. If you put a big number in front of the horizontal, it's going to compress it. If you put a small number, it's going to stretch it. Okay, so anything that's inside the function is always backwards. This is the inside the function in that green box. Vertical is outside the box. Any question on that? Okay, yeah, mixture problem. All right, so we've done mixture problems before. This one's actually, I think it's a little easier because we don't have to set up a system. We're not going to do like we've done before with the system. It's a little different. So one thing that we have to understand how to do, though, is if I tell you you have a 50-ounce container in front of you, and I say that in that container, you have 50 ounces of liquid, 35% of that liquid is acid. The rest of it is mixed in as water. How would you figure out how much is acid if 35% out of 50 ounces is acid? What would you do? Yeah.
Multiply 50 by 0.35.
Yep. So multiply 50 times 0.35. And that means out of the 50 ounces of liquid, there's really only 17.5 ounces of acid. Right? That's one thing that's important to know how to do. Any question on that? Okay, let's look at the problem. So I'm going to take that mixture that I have, and I'm going to pour in X ounces of 100% pure acid. Okay, I'm going to pour that into the mixture I already have. What they're going to want me to do is find a formula that will tell you the concentration. And if you're not sure what concentration is, concentration is, in this particular case, the amount of acid divided by the total liquid. So if you have 50 ounces of acid and you have 100 ounces of liquid, 50 divided by 100, that's a 50% solution. Okay, and we're going to call the concentration C for concentration. Okay, so it says find a graph of the new concentration. So let's start with I know it's going to be C of X because they tell me in the problem I'm adding X ounces. X is the unknown, so I have to use X. Now it's going to be the total amount of acid divided by the total amount of liquid. There's two sources of acid in the problem. One is what was already in the solution. The other one is what we're going to pour in with it. how much acid is already in this solution?
Well, there's X, and then there's the 50 times the 35%.
Right, there's the 50 times the 35%, so there's already 17.5 ounces mixed in. And how much more are we going to add? Yeah, we're going to add X. So when we're done, there's going to be that much acid. X could be 0. We don't add anything. Now we need to divide by the total amount of liquid. How much liquid did we start with? We started with 50. And how much liquid did we add to it? What does the problem say? How much liquid are we adding? Yeah, we're adding X. So that is your new concentration. This is basically the original right there. If you take 17.5 and divide by 50, you'll get 35%. And we're adding in X ounces. Now, concentration is always a percentage, but the way we're doing it here is a decimal. So what do you think, in general, the smallest concentration could be what percent? Like for any solution. That's the smallest that a concentration could be. Yeah?
1%.
Go even smaller than that. Yeah? 0. If I give you a glass of water and say how much acid is in it, well, it could be 0. So it could be a 0% concentration. And what's the highest concentration you can have? 100. It's pure, whatever the chemical is. Most likely it's going to be something in between. So let's graph it. 17.5 plus X. And we're going to divide by 50 plus X. Now, 0 to 100%, that's as a percent. What would that be as a decimal? From concentration, we go from what to what?
0 to 100.
As a percent, it would.
Yeah.
How about as a decimal? Yeah? It's going to go between 0 and 1. Now, in our problem, but in particular our problem, the concentration can't go as low as 0. What's the lowest that the concentration could probably go? It can't go any lower than this. Yeah?
35.
Yeah, it can't go lower than 35% because you're not pouring in water isn't an option. You can add nothing or you can add pure acid. You can't add something to dilute it. So the lowest concentration is 0.35 and the highest is 1. We can't add a negative amount of acid. And the maximum amount of acid you can add, we don't know. Okay, the maximum could be as high as much acid as you have. Maybe you have up to 200 ounces. Will the concentration ever hit 1? Why not?
Because, like, there's already water in there.
Yeah.
You can have 0 water.
Right. It's almost like if I gave you like a white, gallon of white paint and I put a couple drops of black in it. You can't get that black out of it, right? It's in the paint. So no matter how much more white you add, you can dilute it and make it less and less visible, but it's still in there, right? Same thing here. It's still going to have some stuff that wasn't acid to start with. So there's your concentration. The more and more acid you add, the higher the concentration gets, but it's starting to level off. What we want to know is how much acid would you have to add to make the mixture exactly 75%. So it's at 35. I want to get it up to 75. How do you think I would use my graph?
You could do like the trace thing.
We could try to trace, but we might not get exactly at that number. Like if you start tracing, see how the numbers are kind of like 0.79. I want to get exactly 0.75, but I might not be able to get it.
Oh yeah, you can't plug in more.
Yeah, see, I can't get it on 0.75. So I know it's around 80, but how could I get it exact? Yeah.
You could line it at y equals 0.75.
Yeah, make a line at y equals 0.75, and then
Find the contact point.
yeah, find where they cross. And we estimated it's about 80. The exact answer, but yeah, it was 80. But it could be like 80.2. In this case, it's exactly 80.
Couldn't you also open up the table and plug it in?
Well, you can pick numbers to try for x. The problem is if the answer comes out to like 81.347, and I don't know how you're ever going to guess that to try that number.
Well, isn't there a way to like plug in like
0.75?
no to plug it?
No, you can't do that backwards. If there was, then yes, you could. But all you can do is guess numbers for x and see what comes up for y.
Okay.
In this case, you might have guessed it because it's a nice number. But might not always be a nice number. Okay, so that's a mixture problem. Again, I think a little easier than the ones we did before because it's not a system. It's just there's one equation, and that's how it looks every time. All right, so page 207, that's what we did on graphing y1, y2, finding an intersect. We did a few quick problems. And then on page 222, that's 4.1. Okay, reminder, I will be out of school on Thursday, so if anybody needs to stay to make anything up or come for extra help, that's the day I'll be here.